Hi everyone. Today let's talk about the mean value theorem. This is the last of the three existence theorems that we are learning about in calculus. So the first one that we learned about was the IVT, and I'm just kind of listing these up here for comparison. And so remember, the IVT was basically the thing that guaranteed that all your y values are covered between your two endpoints if we're on a continuous function. Remember, that one didn't have anything to do with calculus. We hadn't even learned derivatives yet when we learned the IVT. So that's going to be important later on. And then we learned about the EVT, the extreme value theorem, which is the one that leads us to be able to do the candidates test. Okay. The extreme value theorem just says that on a closed interval of a continuous function, there has to be a highest point and a lowest point. There has to be a maximum and a minimum. And the candidates test is how we find those things. Today we are learning the third, which is the MVT, the mean value theorem. And we'll talk about what that one says in a second. But these three theorems are known as the big three in calculus. These are the existence theorems in calculus land. And they all talk about proving that something exists, proving that something has to occur. So what the mean value theorem says is that, once again, if we are continuous, okay, all these other ones also relied on the fact that the function was continuous. This one also has the additional condition of being differentiable. So you have to be a function that's differentiable, and that should give you a clue that derivatives are going to come into play here. On a closed interval, then there exists a point C between A and B, remember that's what this is saying, such that the average rate of change, A rock, between A and B is equivalent to the derivative at C. Okay, I actually think this one is a lot easier to understand when we talk about it in pictures instead of words. So let's diagram this out. I've got a function over here on a closed interval, a continuous differentiable function. And so let's first talk about this average rate of change of B, right? The average rate of change would be the slope between the two endpoints. So essentially the slope of the secant line, if I were to sketch that in. Okay? So that slope represents the average rate of change. And so what this theorem is saying is that somewhere on this function between these 2 points, there must be a place where the derivative, which remember is also a slope of a tangent line, is equivalent to this slope. So just to give you kind of a visual, here's my ruler, right? That's what my slope looks like. And so not tilting this ruler at all, I should be able to find a place somewhere on this function where the tangent line, I'm guessing it's right about there, where the tangent line has the exact same slope as that average rate of change. Okay? So we're kind of estimating that right here at x equals 1, if I were to draw this tangent line in here, that pink slope would match the average rate of change slope that I marked before. Okay? Essentially, these two lines have to be parallel to each other. Okay? And so what the MVT guarantees is that this magic point, this is point C, has to exist because the derivative at C matches that average rate of change between the endpoints. Okay, so let's put this theorem to use. Example 1. This is the equation, by the way, that's in the picture up above. So we may refer back to this picture as we're doing this, but we're going to do the math here. We've got a function, we've got a closed interval, and it first just says, find me the average rate of change. Okay, so the average rate of change, we know how to do that. If it's on this interval, then essentially what I want is f of 1 minus f of negative 3 over 1 minus negative 3. Okay, we could pull f of 1 and f of negative 3 off of this graph if we want, because we know this is the picture of the graph, right? Or we could be plugging the 1 in up here. Let's see, 1 squared plus 3, so that's 4. 4 minus 2 is 2. And then for negative, and just verifying that over here, if I were to go to where x equals 1, my function value is a 2. This is my x-axis right here. It's kind of hard to see. And then f of negative 3, Well, that would be 9 minus 9, so that's 0, so I think that's negative 2. And again, if I verify here, here is where x is negative 3, right? Yeah, negative 1, negative 2, negative 3, and I'm at a value of negative 2. That axis is numbered kind of strangely, so don't let that throw you off. And then this is over 1 minus negative 3, which is 4. So we have 4 over 4, which is 1. So what that tells me is that's the slope of this blue line, okay? The average rate of change would be 1. And this does have a slope of 1. Remember I said that the graph is numbered kind of strangely, like the axes are not spaced out the same. So it might not look like a slope of 1 to you, but I promise that it is. Okay, does a point C exist such that the derivative at C is equal to 1? Well, that's what the MVT says. It says that if I'm on a closed interval with a continuous and differentiable function, there has to be a point where the derivative is exactly equal to this average rate of change. Okay? So, yes, this point has to exist. We are justifying this using the mean value theorem. So we have to think about those conditions, right, of the mean value theorem. So I would say yes, because f of x is continuous and differentiable. Sorry, these are really long words to be writing in a video. On that interval from negative 3 to 1. Okay. Technically, that's all I have to say. You don't have to name the theorem, but if you were going to, we would kind of tack on something like, so MVT applies. And basically, that's what MVT says, is that this point has to exist. Okay? Okay, so now it wants us to find that magic value of C. We just proved that it was there. We proved that it was a thing. Okay, now we want to find what it is. And this is the part that people tend to miss because they get really good at finding this average rate of change and they want to just stop there. Okay, but what we want here is we want the place, and actually let me write this in a different color. We want to know, where does A rock equal f prime of x? That's what this question's asking, is when does this happen? So we found A rock already, right? A rock is 1. And now I want to find the derivative of this function, okay? Derivative of this function is just 2x plus 3. Subtract the 3, I get negative 2 is 2x. And then divide, and I end up with x equals negative 1. So this is the place where the average rate of change is equal to the derivative. Let's look back at our graph here a second. See that pink line we drew? This is at x equals negative 1. Here's 0, here's negative 1. So we were correct in our placement of this line, that at this point, the derivative is exactly equal to that average rate of change. Okay, let's try another one, kind of from the beginning. Here's example 2. We've got ourselves a function. We've got a closed interval. And it says that k is a point somewhere between 0 and 2, where the slope of the tangent line, or in other words, f prime, is equivalent to the slope between 0 and 2. That's talking about an average rate of change. How do we know this point exists? Well, that would be our friend MVT, right? The mean value theorem. Now, what do we have to know about the function in order to use mean value theorem? We have to know that this function is continuous and differentiable. So, talking about continuity, this graph doesn't, or this function doesn't have any place where we could even have a discontinuity, right? Look out for those denominators being 0 or asymptotes, anything like that. So this is a continuous function. It's a polynomial, right? So it has to be continuous. And then also, the derivative exists. We can take a derivative of this thing anywhere we want. There's no place that we have to worry about a derivative not existing. So we know that k exists because f of x is continuous and differentiable. And again, that's really all you have to say. Okay? We could tack on there. So, MBT applies. But you don't technically have to name the theorem as long as you establish conditions, right? And these are your two conditions for MBT to apply. Okay, so now let's find that value of k. And I want to remind you what we set up here. We are looking for the place where the average rate of change is equal to the derivative. So let's find our average rate of change first, between 0 and 2. So I would want to do f of 2 minus f of 0, whoops, missed my parentheses there, over 2 minus 0. Well, f of 2, 2 squared plus 4, that's 8. And then f of 0, 0 squared minus 4 is 4. All over 2. 8 minus 4, 4 over 2 is 2. The mistake I see a lot is people stopping right there and saying that that's their answer, right? That's your average rate of change. We want to know when is the derivative equal to that average rate of change. So we now want to find our derivative, which actually is a really easy derivative, right? Derivative of x squared plus 4 is just 2x. And I want to know when does that 2x equal this 2, right? I want to know when does average rate of change, oh, sorry, this is average rate of change, equal, well, I don't think I can save that one, f prime of x. Okay, that's what I'm looking for. When does f prime of x equal average rate of change? Well, that's really easy, right? Solve that. Divide, and you get x equals 1. Okay, another one where x equals 1. Actually, I think the last one was -1, but I promise they don't always work out so nicely and perfectly at 1 every time. Okay, example 3. Example 3, I'm a little annoyed with myself with the wording here. Take a quick second and read it. We're talking about filling a coffee mug, right? And we're looking at it over the course of 3 minutes. Apparently it takes 3 solid minutes to fill this 20-ounce coffee mug, okay? What I should have said in the wording of this question is that this function is differentiable, okay? It should make sense to you that this function is continuous, right? Because you can't fill a coffee mug not in a continuous way. You can't suddenly jump from 6 ounces to 10 ounces without covering everything in between. So it has to be continuous. Differentiability would be like if there was some sort of sudden movement, sudden change. So I really should have added to the wording of this question that we're dealing with a differentiable function. Okay? Because that's going to make it so that we can use MBT to answer these questions. So normally in a well-written question, that would be in there. Okay, so I want you to look at the difference between these questions that I have here. The function that I'm looking at is talking about the amount of coffee in the mug or in the thermos at any given time. And the first question I'm asked here just wants to know, is there a place where the amount of coffee is 7.5 ounces? When you're looking at the amount and you're being asked about the amount, there's no calculus involved, okay? You are just looking at these values and saying between 0 and 120, does there have to be a place where the number of ounces is exactly 7.5? And I hope your brain is telling you yes, right? In between 6 and 10, we have to have crossed 7.5. That's using the IBT, right? If we know that our value falls between these two y values, then we know there must be a place, there must be a value up in here someplace where I can say that the exact amount of coffee is 7.5 ounces. So I'm using the IVT here. Don't technically have to name the function, but I'm putting it here for your benefit so you understand what I'm doing. We have to think about the conditions for IVT, okay? The first condition is that our function is continuous. If all I tell you is that it's differentiable, do we also know it's continuous? And I hope you're saying yes, okay? You can't be differentiable without being continuous. So here's how I'm going to answer this. Yes. Since C of t is differentiable, it must be continuous. So not only am I saying it's continuous, but I'm stating how I know it's continuous, right? In this case, if they told me it's differentiable, then it has to be continuous. The other condition for IVT is basically what we wrote up here in pink, that 7.5 falls between these numbers. So I would say, I named this function C of t for coffee. So I'm going to say C of 75 is less than our number of 7.5, which is less than C of 120. Okay. Technically, that's all I have to say. Those are my two conditions for using IVT. I can say that I'm using IVT, but especially when you start using all three of these theorems, it's easy to mix them up and say the wrong one. So I would recommend not naming the theorem. Just make sure you have the correct conditions. And the correct conditions are that we're continuous and that our number falls between these two numbers. Okay. So now when you read the next question, is there a time, this time we're looking between 130 and 180, so we're looking down here, where the amount of coffee, now this does say amount of coffee, but notice it says increasing at a rate. That's a derivative question, right? That's not the function that I'm looking at. I'm being asked about the derivative of this function, okay? And so if I want to know if a derivative exists, this is where we're going to use MBT. And I would know that that derivative exists as long as I know that an AROC exists of exactly this number. So what I'm going to find is the average rate of change on the interval between 180 and 130. So C of 180 minus C of 130 over 180 minus 30. I'm sorry, 130. Okay, and that would just be 20 minus 12 over 180 minus 130 would be 50. So that's 8 over 50, which, hey, look at that. That's going to be 16 over 100, which is 0.16. Okay? So since I know the average rate of change is 0.16, MBT says there has to be a place where my rate of change is exactly this number, right? And so I need to establish my conditions for MBT, which is that the function is continuous and differentiable. So, yes, C of t is differentiable, so it is also continuous. Notice how I linked those two together. I didn't just say continuous and differentiable, because all I really know is that it's differentiable. So, kind of like I did up here, I'm establishing that being differentiable means that we're continuous. Is also continuous. And I'm basically just going to say in words what I just did here. The average rate of change on that interval, 130 to 180, is 0.16. I guess we could label it, right? This would be ounces per second. Okay. And the conclusion of that statement, I mean, I don't have to write it because it's really just restating the question. But the conclusion of that is, so therefore, there must be a place between 130 and 180 such that the instantaneous rate of change is exactly 0.16. The derivative is exactly 0.16. This, by the way, is the theorem that allowed us to do all of that estimating of derivatives that we did earlier this year. So I was giving you questions like this earlier this year, and I would say, estimate the derivative at 140. And you couldn't see 140, but you did like an average rate of change between 130 and 150, and we said, that's good enough, even though we knew it wasn't really a derivative. The reason that worked is like that answer that we got, that average rate of change, it might not have been the derivative right at 140, but it was definitely the derivative somewhere between 130 and 150. And so that's why that estimate works, is we were saying that's close enough to 140, that derivative has to exist in there someplace. Okay, so that's about it for MBT. Really, the math is not hard here. The justification sometimes will catch you. And remembering that, well, not so much with this example, but with something like this, you can't just stop at finding average rate of change, right? You're setting the derivative equal to the average rate of change in solving. Okay, that's it for this lesson. Thanks a lot. Have a great day.